more full-color images from the James Webb Space Telescope. Mark Strassman has a look at the birth of the universe.
The James Webb Space Telescope has just delivered an astonishing revelation. Something massive has collided with Neptune. The detection did not come as a faint hint or minor anomaly, but as a clear and undeniable signal that one of the most distant planets in our solar system had just experienced an event of cosmic proportions. Neptune, often called the ice giant because of its composition and distance from the Sun, is a world of mystery even after decades of telescopic study. But never before has humanity witnessed a confirmed collision of such magnitude in its vicinity. What Webb saw was not just a planetary disturbance, but a monumental celestial event that has set scientists and observers buzzing with excitement and questions. Before we start, smash the like and subscribe buttons for more updates. The telescope's infrared sensitivity is what made this detection possible. While Neptune lies far beyond the reach of most Earth-based instruments in terms of fine detail, Webb's powerful optics and advanced instruments allow it to pierce through the cold darkness of the outer solar system. Through those lenses, faint energy patterns, heat signatures, and atmospheric ripples are transformed into detailed observations. When Webb trained its gaze on Neptune, expecting routine studies of clouds and atmospheric dynamics, what it captured instead was evidence of a sudden and violent impact. The telltale signs were unmistakable. Shock waves in the planet's upper atmosphere, heat blooming where normally only cold methane haze dominates, and irregular movements that indicated a disruption far beyond normal weather patterns. The scale of the object that collided with Neptune must have been gigantic. For something to leave such a visible mark on a world more than 17 times the mass of Earth, the impacting body would need to be vast, perhaps comparable to a small moon or a large dwarf planet. The Kuiper belt, a region beyond Neptune filled with icy bodies and primordial remnants of solar system formation, is the most likely source. This belt harbors objects hundreds of kilometers across, drifting silently for billions of years. If one of these massive wanderers strayed too close to Neptune, gravitational forces could have pulled it in, accelerating it to unimaginable speeds before it slammed into the ice giant's atmosphere. The result would be an explosion releasing energy millions of times greater than the largest volcanic eruptions on Earth, a cosmic upheaval powerful enough to reverberate across the planet. The immediate implication of such an impact is the reshaping of Neptune's atmosphere. This world is known for having the fastest winds in the solar system, whipping around at over 1,500 miles per hour. The introduction of an enormous external body would disrupt those jet streams and create chaos in the distribution of clouds and storms. Webb's instruments showed turbulent zones spreading outward from the impact site, towering storms that climbed higher than any seen before, and thermal hotspots glowing in wavelengths invisible to the human eye. These disturbances are not fleeting. They could linger for decades, leaving a long-term signature of the collision that future observatories will track with great interest. The event also highlights the dynamic and unpredictable nature of our solar system. For centuries, Neptune has seemed like a serene, distant sentinel on the edge of the Sun's influence. But what Webb has revealed is that even out here, nearly 3 billion miles from Earth, the forces of creation and destruction are very much alive. Collisions were once thought of as relics of the solar system's violent youth, when planets were still forming and impacts were routine. Yet here is proof that such dramatic encounters are not only possible but inevitable, even in our present cosmic age. The solar system remains restless, and its giant planets still interact with the wandering debris left over from its birth. The implications extend beyond Neptune itself. Studying the aftermath of the collision will teach scientists how impacts shape planetary atmospheres and interiors. Unlike Earth, where erosion and tectonics erase much of the evidence of ancient collisions, Neptune is a pristine laboratory. Its thick atmosphere records disturbances in patterns of circulation, cloud formation, and thermal anomalies. By monitoring how these evolve, astronomers can gain insight into how impacts might have influenced the development of early Earth, Mars, and even the gas giants. This event is like a live experiment, showing in real time what sort of consequences a massive impact has on a planetary scale. There's also the matter of scale and rarity. Impacts of this magnitude are exceedingly rare, occurring perhaps once in many millions of years for any given planet. To witness one within the span of human observation is extraordinary. That Webb happened to be trained on Neptune at precisely the right moment suggests both a stroke of luck and a testament to its powerful monitoring capabilities. It raises the possibility that other planetary collisions have occurred unnoticed in the past, beyond the reach of our instruments. With Webb's unprecedented vision, these once hidden events may now become part of our observable universe, offering us direct windows into processes that were previously only theorized. This detection further underscores Neptune's importance as a planetary system. The planet hosts a faint but complex set of rings, multiple moons, and a magnetic field tilted drastically from its rotational axis. Any major collision could have ripple effects across this entire system. Moons might experience altered orbits due to gravitational shifts. Ring structures could be disrupted, feeding new material into space or reshaping the arcs of dust and ice already circling the planet. Webb's observations may soon reveal subtle changes in Neptune's satellites, particularly Triton, its largest moon, which itself is thought to be a captured Kuiper belt object. A giant impact on Neptune could resonate across its moon, subtly altering the delicate balance that has held for eons. The energy released by such a collision would also penetrate deep into Neptune's atmosphere, perhaps reaching its mysterious interior. Unlike Jupiter and Saturn, Neptune radiates far more heat than it receives from the Sun, a clue that it has a dynamic, active core. Scientists have long debated the source of this excess heat, but a fresh injection of energy from an enormous impact could temporarily alter that balance. Webb's infrared imaging might track changes in Neptune's thermal output in the months and years to come, revealing how such a disturbance influences its deep structure. It is an unparalleled opportunity to probe beneath the icy veil and learn what truly powers this enigmatic planet. From a broader perspective, the collision is a reminder of cosmic vulnerability. While Neptune bears the brunt of this particular impact, it raises the question of how often such events occur closer to home. Earth has been struck by massive bodies in the past, the most famous being the impact that likely ended the reign of the dinosaurs 66 million years ago. Seeing a giant collision on Neptune is a sobering reminder that our planet is not immune to such encounters. By studying what happened on Neptune, we might better understand the risks to our own world and refine our ability to predict or even prevent future catastrophic impacts. For planetary scientists, the excitement lies in the data-rich opportunity that Webb provides. Every ripple in Neptune's clouds, every thermal hotspot, and every shift in its atmospheric chemistry can now be measured with precision. This data can be fed into computer models, allowing researchers to reconstruct the size, speed, and composition of the impactor. Was it an icy body from the Kuiper belt rich in frozen water and methane? Or was it a rocky object flung inward from even farther reaches of the solar system? Answering these questions will help refine our knowledge of the distribution of material in the outer solar system and the dynamics that occasionally send such bodies hurtling toward planets. The collision also connects to the larger narrative of planetary defense and exploration. If Webb can detect and monitor such an event at Neptune, it suggests that future telescopes could watch for smaller but still dangerous impacts closer to Earth. It demonstrates the importance of having instruments capable of surveying not just deep space galaxies, but also our own planetary backyard. The boundary between astronomy and planetary science has blurred, and every new observation serves both to expand our understanding of the cosmos and to safeguard our place within it. In terms of pure wonder, the image of something gigantic colliding with Neptune captures the imagination like few other cosmic events. The distant blue planet, often overlooked in favor of its brighter siblings like Jupiter and Saturn, has suddenly become the stage for one of the most dramatic astronomical moments in living memory. It reminds us that every world, no matter how remote, is a participant in the ongoing dance of creation and destruction that defines our universe. Neptune is no longer just a distant speck of icy mystery. It is now a witness to an impact of colossal proportions, its atmosphere carrying the scars of an event powerful enough to reshape it for generations. As Webb continues to monitor the aftermath, scientists and the public alike will be glued to its findings. Each new observation will add layers of understanding to the event and deepen our appreciation of the interconnectedness of the solar system. Neptune's collision is more than just a distant spectacle. It is a profound demonstration of the forces that govern planetary evolution. It is a moment when theory has become reality, when a world nearly 3 billion miles away has reminded us all that the universe is never static, and that even the most distant planets can surprise us with drama and magnitude beyond imagination. The James Webb Space Telescope's detection of a massive collision on Neptune has opened an entirely new frontier of exploration, and the deeper one delves into the implications, the more profound the revelations become. What has been glimpsed is not a simple planetary disturbance, but a rare natural experiment unfolding before human eyes. The great ice giant, often overshadowed by Jupiter and Saturn, is suddenly at the center of attention. It is not only a distant planet cloaked in methane-rich atmosphere, but also the site of an event that could redefine how scientists think about planetary dynamics, solar system evolution, and the restless interactions between celestial bodies. To appreciate the scale of this occurrence, one must first imagine Neptune as it exists in its natural environment. It is a world of extremes, perched on the fringes of the solar system, bathed in faint sunlight that is 1,000 times weaker than what Earth receives. Its deep blue hue comes from methane molecules that absorb red light, giving it an appearance that has long fascinated astronomers. Yet beneath that serene exterior lies an atmosphere whipped by hurricane-like storms, supersonic winds, and a volatile balance of gases. Into this volatile world came the intruder, a gigantic body likely pulled from the icy wilderness of the Kuiper belt. The sudden transfer of momentum, energy, and material into Neptune's fragile equilibrium marks an event so extraordinary that every fragment of data harvested from it will be priceless. One of the most significant aspects of the collision is the insight it provides into atmospheric shock dynamics on a planetary scale. When an object of such magnitude enters Neptune's atmosphere, it does not simply disappear into the gaseous depths. Instead, it compresses the atmosphere in front of it at tremendous speed, generating shock waves that ripple outward. These shock waves heat the surrounding gas, creating localized thermal surges visible in the infrared spectrum. Webb's ability to capture these surges means that, for the first time, scientists can observe how an alien atmosphere responds in real time to a devastating external blow. On Earth, atmospheric entry of meteors has been studied through historical events like the Tunguska blast or the Chelyabinsk meteor. Yet those are minuscule compared to the scale of what happened on Neptune. Observing how a giant planet's atmosphere absorbs and disperses such energy will refine theoretical models in ways terrestrial events never could. Another compelling angle is the chemistry of the aftermath. Neptune's upper layers are dominated by hydrogen, helium, and methane. Introducing a foreign body, potentially composed of water ice, carbon-rich compounds, or silicate rock, injects new chemical ingredients into that mix. As shockwaves churn the atmosphere, they catalyze reactions that would otherwise remain dormant. Methane molecules may fracture, recombining into more complex hydrocarbons or carbon soot. Water vapor from an icy body could interact with existing gases to form exotic compounds under the intense pressures and temperatures. Webb spectrometers can detect these chemical fingerprints, giving humanity a front-row seat to the creation of molecules under extreme conditions. In some ways, this is a miniature version of the processes thought to have seeded Earth with the building blocks of life billions of years ago. Neptune's collision becomes not only a lesson in planetary physics, but also in cosmic chemistry, a live demonstration of how the raw materials of complexity emerge from violent encounters. The scale of energy release also compels reflection on the internal structure of Neptune. Beneath its thick atmosphere lies a mantle rich in water, ammonia, and methane ices, overlaying a rocky core. The impact would not have stopped at the upper layers, but penetrated deeper, sending shock fronts cascading toward the mantle. Such energy could temporarily alter the convection currents that transport heat from Neptune's interior. This might explain any sudden increases or anomalies in Neptune's already puzzling thermal emissions. For decades, scientists have noted that Neptune emits more than twice the energy it receives from the Sun, a discrepancy not fully understood. The collision may provide a natural experiment to see how external inputs of energy interact with whatever internal mechanism drives that excess heat. If Webb's instruments detect changes in Neptune's infrared glow over the coming months, it may bring us closer to solving a mystery that has lingered since Voyager 2 flew past in 1989. Beyond Neptune itself, the collision reverberates into broader questions of solar system dynamics. The Kuiper belt is not a static zone, but a reservoir of icy bodies orbiting in complex resonances with Neptune's gravity. For one of these bodies to strike the planet suggests shifts in the long-term orbital ballet occurring at the solar system's edge. Such a strike raises questions about whether gravitational interactions with Neptune itself destabilize the object's orbit, whether unseen perturbations from farther afield nudged it inward, or whether chains of resonant interactions set the stage. Understanding this pathway could yield insight into how often such collisions are likely, not only on Neptune, but across all the giant planets. The solar system's outer reaches are still poorly mapped, but the collision highlights the urgency of charting that territory, as these bodies occasionally become dramatic agents of change. The event also touches upon the story of Triton, Neptune's largest moon. Triton is unusual among major moons because it orbits Neptune in a retrograde direction, suggesting it was once an independent Kuiper belt object captured long ago. The collision that Webb detected may have eerie echoes of the ancient past, when Neptune first seized Triton from its solitary voyage. That ancient capture is thought to have destabilized Neptune's original moons, leading to catastrophic collisions and the rearrangement of its entire system. Today's impact, though smaller in scale, resonates with that narrative. Neptune continues to interact violently with Kuiper belt material, shaping its destiny in fits and bursts of cataclysm. It raises the possibility that Triton itself may bear scars of past impacts, locked in icy crustal layers waiting for future missions to uncover. Perhaps most fascinating is the way this single event links Neptune to the broader exoplanetary frontier. Around other stars, astronomers have cataloged thousands of Neptune-like planets, ranging from slightly smaller mini-Neptunes to larger sub-Saturns. These planets are among the most common in the galaxy, yet their formation, evolution, and atmospheres remain enigmatic. By watching how Neptune responds to an enormous impact, astronomers obtain a living template for interpreting distant worlds. If a young exoplanet exhibits unusual heat signatures or strange atmospheric chemistry, perhaps a collision is to blame. What Webb has given us on Neptune may ripple outward into our understanding of planetary systems across the cosmos, linking our backyard to the vast galactic neighborhood. There is also the question of Neptune's rings, often overlooked in discussions of the planet. Though faint and narrow compared to Saturn's grand display, Neptune's rings are intricate structures composed of dust and ice. An impact of this scale could easily disturb them, either by ejecting material from the planet's atmosphere into orbit, or by gravitationally altering existing ring particles. If Webb observes new arcs or unexpected thickening in Neptune's rings, it could indicate that material from the collision has joined the dance. Such a process would provide direct evidence of how planetary rings evolve through external events. Since rings are thought to be transient features in the lifespan of a solar system, replenished or destroyed by impacts, Neptune's collision offers a rare chance to study this replenishment in progress. Even Neptune's magnetosphere may not escape unscathed. The planet's magnetic field is famously tilted by almost 47 degrees relative to its rotation axis, a configuration that produces complex interactions with the solar wind. A massive collision could inject charged particles into that environment, temporarily intensifying auroras or creating disturbances detectable from afar. Webb, though not designed as a magnetometer, might still pick up indirect evidence of these disruptions through changes in atmospheric emission. For planetary scientists, this is a reminder that impacts do not only affect surfaces and atmospheres, but can also ripple through invisible electromagnetic environments, altering the planet's interaction with its star. In addition to the scientific harvest, the cultural and philosophical impact of this event cannot be underestimated. Human beings have long imagined planets as distant, unchanging spheres, serene in their slow orbits. To witness a massive collision on Neptune is to shatter that image and confront the truth that these worlds are dynamic, vulnerable, and in constant flux. It speaks to the raw power of nature on scales beyond comprehension, where objects hundreds of kilometers across can slam together in silence, their violence unfolding in a realm where no human ear can hear, but where the consequences reverberate across the solar system. It forces reflection on our place in that system, reminding us that Earth itself is part of this cosmic lottery. For educators and communicators, Neptune's collision is a gift of storytelling. It combines drama and science in a way that captivates imagination. A giant blue world, struck by an enormous wanderer from the dark edges of the solar system. Its skies lit with shock waves, its clouds reshaped, its chemistry altered. This is the kind of narrative that inspires new generations to look skyward, to pursue careers in astronomy, physics, and planetary science. The James Webb Telescope, already celebrated for its views of distant galaxies and the faint light of the early universe, now demonstrates its equal power to transform our understanding of the solar system right at home. Looking forward, the collision raises tantalizing prospects for future missions. While Webb observes from its perch at L2, closer probes may one day be dispatched to study Neptune directly. Concepts for orbiters or atmospheric probes have floated in space agencies for decades but never advanced due to budgetary and priority constraints. Now, with Neptune suddenly thrust into the spotlight, momentum could build for a mission dedicated to unraveling its mysteries. Such a mission, arriving years after the collision, would study the lingering scars, track the chemical aftermath, and perhaps land on Triton to compare its icy surface to Neptune's disturbed skies. The collision may become the catalyst that finally propels humanity toward a dedicated exploration of this distant world. At the same time, theorists will eagerly model the event, reconstructing the trajectory of the impactor, its likely origin, and the physics of the strike. Did the object spiral in over millennia, nudged inward by Neptune's gravity? Or was it abruptly perturbed by a chaotic resonance? Was it a solitary body, or did it represent the vanguard of a larger flux of material destabilized in the Kuiper belt? These questions touch upon deep issues in celestial mechanics and the architecture of the outer solar system. The answers will refine models not just of Neptune, but of the entire population of icy bodies beyond it. What Webb's discovery makes clear is that Neptune is no longer a distant afterthought. It is now an active theater of planetary science, where forces once thought confined to the solar system's early history still play out with breathtaking scale. Each passing month will likely bring new insights as the collision's aftermath evolves. Storms that spread, rings that shift, emissions that fluctuate. The James Webb Telescope has not only witnessed the collision, but has become the chronicler of its unfolding legacy, ensuring that this event will not fade into obscurity, but will remain a landmark in the study of planetary systems. It is remarkable to consider that had Webb not been watching, the event might have gone unnoticed entirely. Neptune is so remote and its atmosphere so opaque that Earth-based telescopes would likely have missed the telltale signs. This underscores the importance of having instruments that can continuously monitor the outer planets, bridging the vast distances with unblinking eyes. Just as the Shoemaker-Levy 9 comet impact on Jupiter in 1994 revolutionized understanding of planetary collisions, Neptune's collision in the Webb era will become a defining moment in 21st century astronomy. The James Webb Space Telescope's detection of a colossal collision on Neptune is already reshaping how scientists think about the outer solar system, but the implications stretch far beyond the immediate spectacle of impact. To push further into the significance of this moment requires examining Neptune not just as a solitary world, but as a nexus of scientific puzzles that have long lingered without resolution. With Webb's capabilities, this event provides a rare portal into questions about planetary architecture, cosmic evolution, and the forces that continue to shape the solar system even billions of years after its birth. Neptune has always carried with it an air of enigma. When it was discovered in 1846, it wasn't through direct observation, but rather through mathematical prediction. Astronomers noticed irregularities in Uranus's orbit, suggesting the presence of another massive body tugging invisibly at it. Neptune's discovery became a triumph of human reasoning, proof that unseen worlds could be found through the subtle fingerprints they leave behind. In a sense, the recent collision echoes that story. What Webb has captured is another invisible hand at work, this time not of a planet disturbing an orbit, but of a massive body disturbing an entire atmosphere. The fact that Neptune once revealed itself through its gravitational pull and now reveals its dynamism through a violent impact is a poetic reminder of the layered ways in which this planet continues to surprise. The collision also brings into sharp focus the question of time. Neptune orbits the Sun at an immense distance, completing a single revolution every 165 Earth years. Human lifespans can barely measure a fraction of its seasonal cycle. To witness a sudden, catastrophic event on such a slow-moving world is to be reminded that planetary time is both immense and punctuated by rare, decisive moments. Impacts are punctuation marks in the long narrative of a planet's life. They occur infrequently, but when they do, they alter the trajectory of the story in ways that last for eons. Observing one on Neptune is akin to catching a glimpse of a thunderclap in an otherwise still landscape, a reminder that even the slowest moving worlds are never static. The sheer violence of the impact also forces scientists to reconsider the thresholds of planetary resilience. On Earth, life exists in a delicate balance. A collision of even moderate size can trigger extinctions, shift climate, and rearrange ecosystems. On Neptune, the scale is vastly larger, and yet the planet persists, absorbing the blow without catastrophic disintegration. This speaks to the resilience of giant planets, whose immense mass and gravity allow them to act as cosmic shock absorbers. In fact, such impacts may play a role in preserving the stability of the solar system as a whole. By capturing or absorbing rogue bodies that might otherwise travel inward toward the terrestrial planets, Neptune acts as a guardian of sorts. The recent collision underscores that protective role, a reminder that without the gas and ice giants, Earth might face far more frequent bombardment. Another avenue of reflection concerns the unseen population of bodies wandering in the outer solar system. The Kuiper belt, along with the more distant scattered disk and Oort cloud, contains untold numbers of icy objects ranging from tiny fragments to dwarf planets like Pluto and Eris. Most remain undetected, their faint glimmers drowned out by distance and darkness. Yet the impact on Neptune proves that these objects are not idle relics. They are active participants in the solar system's ongoing evolution. Every time one collides with a major planet, it alters not only the struck world, but also the statistical picture of how the solar system operates. By reconstructing the impactor's likely size and composition, astronomers can refine models of how much material is still drifting in these far-flung regions. The collision is thus not just an isolated event, but a data point in the vast ongoing census of solar system debris. The implications ripple outward into comparative planetology. Jupiter, Saturn, Uranus, and Neptune form a family of giants, each with its own quirks and mysteries. Jupiter has already shown humanity the scars of impact, most famously in 1994 when fragments of comet Shoemaker-Levy 9 plunged into its atmosphere, leaving dark blemishes visible even from small telescopes on Earth. Saturn has long fascinated scientists with its rings and their enigmatic origin, possibly tied to the breakup of a massive moon. Uranus remains tilted on its side, perhaps due to an ancient collision so titanic that it reoriented the entire planet. Now, Neptune joins this lineage, not with ancient speculation, but with live observation. Taken together, the four giants tell a story in which impacts are not rare accidents, but central players in their evolution. For Neptune in particular, the role of impacts may help explain some of its most puzzling features. Its extreme winds reaching supersonic speeds remain unexplained by solar heating alone. One possibility is that periodic impacts inject enough energy to help sustain these winds over long timescales. If this recent collision can be shown to alter wind patterns in measurable ways, it could confirm that impacts act as long-term drivers of Neptune's meteorology. Similarly, Neptune's irregular ring arcs, which have puzzled scientists since Voyager 2's flyby, might owe their formation or maintenance to collisions supplying new material. What Webb has observed could therefore be a missing link connecting Neptune's present-day quirks to the violent processes that sculpt them. Looking outward, the Neptune collision also sharpens humanity's understanding of planetary defense closer to home. Earth is shielded in part by its atmosphere, which burns up many small meteors, but it remains vulnerable to larger impacts. The Chicxulub impactor that ended the age of the dinosaurs was only around 10 kilometers wide, tiny compared to the body that just slammed into Neptune. Yet its consequences were global. By observing how Neptune's vast atmosphere responds to something much larger, scientists gain insight into the scaling laws of impact physics, how energy distributes through gases, how shock waves propagate, and how chemical reactions unfold are all questions with relevance not just for Neptune, but for Earth's preparedness. In this sense, the collision is a natural laboratory for planetary defense, conducted on a scale impossible to simulate in human facilities. The event also has implications for theories of planetary migration. Models of solar system formation, particularly the influential NICE model, suggest that Neptune once migrated outward, scattering Kuiper belt objects in the process. Some of those objects may have been captured as moons, while others were ejected entirely from the solar system. The recent collision could represent a continuation of that ancient narrative, a body finally catching up to Neptune after billions of years of gravitational entanglement. If so, the event is a living trace of Neptune's migratory past, a fossil of motion written in a single moment of impact. Understanding its trajectory could help reconstruct how Neptune and its siblings reshaped the solar system's architecture long after their birth. Culturally, Neptune has often lived in the shadow of its neighbors. Saturn dazzles with rings, Jupiter dominates with size, Mars captures imaginations with the possibility of life, and even Uranus, with its odd tilt, has drawn intrigue. Neptune, distant and faint, often recedes into the background of public awareness, yet the Webb detection thrusts it into the limelight, and rightly so. It reminds humanity that every planet has its moments of drama, and that the quietest worlds can suddenly become the most riveting. For artists, writers, and dreamers, the image of a distant blue giant absorbing a massive collision is fertile ground for imagination, a narrative of beauty and violence unfolding where no human eye can see directly. If you liked this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on Neptune's collision? Scientific breakthrough or possible cosmic threat ahead? We want to hear from you. Thank you for watching and see you next time.